recording.
Perfect.
All right, let me
Yep.
this. All right, we are 1, 2, 3, officially start. Hello, everyone. Welcome. Thank you for joining GameCrafters, solving the world's board games with computational game theory. Dr. Dan Garcia is a teaching professor in electrical engineering and computer science department at UC Berkeley. Selected as an ACM Distinguished Educator in 2012 and ACM Distinguished Speaker in 2019. He has won all 4 of the department's computer science teaching awards and holds the record for the highest teaching effectiveness ratings in the history of several of the department's courses. He is a national leader in the CS for All movement, bringing engaging computer science to students normally underrepresented in the field. Dr. Dan Garcia is a rockstar professor. He is no stranger to being featured in national and local news for his teaching effectiveness. You might have even seen him recently at the center of a story on NBC Bay Area for overcoming the challenges of remote learning by conducting his lectures with innovative creativity. So please welcome with me, Dr. Dan Garcia.
Thank you so much. Good to see everybody. If folks want to turn their videos on, you can be muted, but it'd be great to see faces of people. It's always great to see the audience. I see one person, so maybe I'll see a mark and I'll see my meet. But if anybody else wants to turn their video on, it'd be great to see other faces and smiling faces. Great to be here, folks. I'm delighted to share this lecture about a research group I've been working with. I started in 2001, so we're going on a 20th year, and the goal is to solve the world's board games. And I've given this talk several times, but I'm delighted to give it again. So let me share my screen. I'm going to share my entire desktop, and that way you'll see this hopefully you see the huge window of my PowerPoint. Do you see that? It's hard for me to see what you see, but do you see the about ACM thing here? Is that right? Perfect. Okay. Perfect. So let me go here and start this. All right. So I was asked as part of the Distinguished Speakers program to have these 2 slides up. So I want to make sure that I honor that request. So ACM is the Association for Computing Machinery, and it's the premier global community of computing professionals and students with nearly 100,000 members in more than 170 countries, interacting with more than 2 million computing professionals worldwide. It's the umbrella organization most of us are associated with. Our mission is to help computing professionals be their best and most creative. We connect them with their peers to what the latest developments inspire them to advance the profession and make a positive impact on society. Our vision: we see a world where computing helps solve tomorrow's problems, where we use our knowledge and skills to advance the community profession and to make a positive social impact throughout the world. And I certainly am proud to be an ACM member. And this is brought to you by ACM. So again, thank you to the Distinguished Speakers program for bringing me in here virtually. So again, my name is Dan Garcia. I'm going to talk about this project I've had called GamesCrafters, solving the world's board games with computational game theory. And I always start with news, computing in the news. And in fact, I encourage all educators on this call to do that, to include computing in the news in your classes. And so this is some news that's a little bit older, out of date, but I wanted to share it because it's relevant to game theory, that checkers, a game that I used to play as a kid and many people have played for years, has been solved by Professor Jonathan Schaefer at the University of Alberta in Canada. And he used dozens, sometimes hundreds of computers and AI to prove that in perfect play, this is a draw. This is what we call weakly solved, which means he didn't visit every position. He didn't visit the entire game tree, but he was able to prove that the game will be a draw if played by 2 perfect players. And you can actually prove things about a game without visiting everything. So he actually has there's a link here, and he has an online system that lets you play it. And if you go online, you can play this game. It'd be really fun to see if you enjoyed that or not. And he has some write-ups he's done about how he did the solving of that. Imagine a 19-year project. Most of our undergraduates aren't 19. So imagine a project longer than you were alive for many of our students. Pretty exciting. So if you were to say, hey, I heard this great talk by Dan Garcia on game theory, your friends might say, oh, you mean economic game theory or combinatorial game theory or computational game theory? And if you didn't know, I want to make sure you know what those 3 are. To say, no, it wasn't economic or combinatorial. It was combinatorial. So hopefully you can see my cursor. Economic game theory is what they offer Nobel Prizes in. They recently offered Nobel Prizes in this because this studies a class of games that are often, or almost always, simultaneous moves. If you're bidding on a house, you're putting your bids on a piece of paper and you submit them as a closed bid. If you are playing rock, paper, scissors, shoot, you're playing an economic game theory game. You don't know what they're doing, they don't know what you're doing, and you have to kind of think about what they might do, and they think about what you might do to have optimize your winnings. So the goal is often to maximize payoff. If you've ever heard of the prisoner's dilemma, this is a economic game theory game. Combinatorial games are games, if you've ever heard of these NIM, domineering dots and boxes, lots of games that are in this, CALES, that are in this category. And this category is games that are two-player games. We'll get to that at the next slide. Two-player games of no chance. But here, the goal for every one of these games is to get the last move. Or in some games, it's the most points. Like in dots and boxes, you get the most points. It's not about the last move, it's about the most points. So only those rare kind of games that end those ways, with the most points or getting the last move, can you consider being a combinatorial game. A computational game theory game considers a larger class of games, but we don't go in as deep into the value of the game as combinatorial game theory games do. So here we consider tic-tac-toe. By the way, Othello is a game that could be a combinatorial game because at the end of the day, I have some number of black squares, you have some number of white squares, and there's a point associated with it. So that actually could be combinatorial in that sense. Connect 4, though, is about getting 4 in a row, and that could not be combinatorial. So computational game theory means we use the power, the sheer brute force of computers to exhaustively search our games and to have a final value. And our values are different than combinatorial games because they consider a larger space of games. We just care about winning, losing, tie, or draw, and they consider the value, which might be a number. It might be they're called surreal numbers, and so that's a little different, a little bit more complex than we do. So I'm just talking in this talk about computational board games. What do you mean by board games? Well, any game that we consider can have no chance. So there can be no randomness. There's no dice, no shuffled cards. So no shuffled cards or dice. Both players know all there is to know about the board, or about whatever the position is. There's no hidden information. Stratego is a game that has no chance. If you ever play Stratego, and Battleship is the same way. There's no chance. You put up your ships your way. I put up my ships my way. But the problem is, I don't know what you've done and you don't know what I've done. So we're kind of guessing, and I'm kind of, oh, is it A4, miss, and I'm guessing. I don't want to have any guessing in these games. So there's no hidden, that's called hidden information. Where your ships are is hidden information, just like Stratego, where your army is hidden information. We don't consider those games. So they have to, if you played Battleship or Stratego with all the pieces face down so I could see everything, then that would be a game we could consider. Two players, left and right, we call them left or right, X or O, black or white, usually alternate moves. They don't always have to alternate moves. You can have a skip move. So in the game of Othello, you can have a position where one person has no more moves and they say skip. And then it's the same first person's turn again. And then they move 2 times in a row. And that'd be fine. You can have those moves. That's fine. But you cannot have a simultaneous move like rock, paper, scissors, shoot. You can't do that because that's a simultaneous move. And I don't know what you're going to do and you don't know what I'm going to do. And the game can end in any way. Remember, we're more general than a combinatorial game, but the game can end any way. So here's how we do it. How do we solve these games? I'm going to show you a little snippet from a video, War Games. This was a feature film in 1983 starring the young child star Matthew Broderick, who went on to star in The Producers and other things. I think he's married to Sarah Jessica Parker. And he, when he was, I think, 16 or 17 years old, was a child actor. And he played some kid who had accidentally hacked into a defense computer called the Whopper. He was just playing around. And what he did was accidentally, he didn't intend it, he's an innocent kid, accidentally set forward in motion. This Whopper started going crazy. It ran amok. And what it meant was it tried to hack into the security codes to unlock the codes for the defense missile system to bomb Russian. But back in 1987, actually 83, that was our opponent. So you're seeing the team try to teach the computer that going to war, this is why it's called War Games, is a bad idea. And they want to teach it that by having it play tic-tac-toe against itself. So I'm showing you what we do, which is we play tic-tac-toe against itself. Let's just show you this here. Here we go. Oops. And I don't know. So tell me if you can hear anything. Go. No, yes, can you hear?
I'm not hearing
I can't hear anything.
No. Okay. So sorry about that. When I shared initially, I didn't click the audio button. Let me do that again really fast, and I'll get that back in there. And I knew I was missing something. Here we go. All right, share the screen, go. And then hopefully this will work. Let's give this a shot. If not, we can just watch the video. We can just watch the, okay, here we go. Boink. Okay, and let's try this again.
Tick, tack, toe.
Kind of like lagging. No.
You're in. Order to disarm the missiles.
No.
5 numbers. It's got half the code.
Sorry?
Put X in the center square.
No.
Six up.
There's no way you can win that game.
I know that. It doesn't. It hasn't learned. Is there any way to make it play itself?
Yes, number of players 0.
Listen to the music. Here we go. Now the music comes in. So now you're watching it play itself in tic-tac-toe. And every time it's playing, it's remembering what it did. It's trying a different strategy and another strategy. And it's actually learning without telling you how machine learning works. This is in 1983. It's practicing and doing it and playing every possible game against itself. This is exactly what my system does. It walks the entire game tree, and pretty exciting. Here we go. And then eventually, let's watch what happens. It got the code, it's gonna launch. I can stop this in a second. Okay. Okay, I have a little glitch in the video. All right. So I showed you that because I wanted to show you what was happening internally in the machine learning sense. What it was doing is it was trying, this is by the way, the definition of a winning position, a losing position, a tie position, and a draw position. I'm going to use my iPad if I can annotate on top of this. So here's what the math is behind everything you're seeing. And I'll use blue because blue has no semantic meaning here. So here's the idea. We're assuming we're all in alternating play. And this is for most games. I play, you play, I play, you play. We're assuming that, okay? And this is the value to the person whose turn it is. So this is really important. For the player whose turn it is. You are a winning position. So for every position, you are a winning position. By the way, just to let you know, arrows are moves. So these are moves. And these circles, these are positions, okay? Positions. So a move is like a change, like a go in the corner square, that's a move. Move your knight to e4, that's a move. A position is a photograph of the board, okay? So that's what that is. So the value, you are winning, let's actually see if you just make sense in terms of the logic of it. You are a winning position if there exists a winning move. And because we're always alternating play, a winning move means you give your opponent a losing position. So all that needs to be is just one. Just one. If you have one winning move yielding a losing position for your opponent, you are a winning position. And by the way, who's ever seen, this is the audience response time. Let me turn on the chat so I can see if anybody's typing. Where have you ever seen these colors I'm using? Green, red, and yellow. When have you ever seen that before? This would be a time for anybody to unmute and tell me or type into the chat. Where have you ever seen?
Stoplight.
A stoplight, exactly.
Traffic lights.
Traffic light, beautiful. So in which green is good, right? Green is good, go. Red is bad, stop. And yellow means accelerate. Oh, no, sorry, California. That was California. No, yellow means tie, so that's somewhere in the middle, okay? So here we go. So winning is good. Remember that. So I am a good winning move if there exists a winning, when I'm a winning position, if there exists a winning move, yielding a losing bad red move for my opponent. Okay. I am a losing position. Here's the losing position. If every single move is bad. It's like you're in the corner and you have no good options, which means all my children, all the people, all the positions that would be yielded for the other player is a winning. So I'm a losing position if all the moves I make, whatever I do, the other person's going to win. Okay. A tie is in the middle, and we have ties in tic-tac-toe, so we'll talk about that. A tie says, well, I don't have a losing child. I'm looking for a losing child. I don't have that. I don't have one of these. But I'm a losing child, then what do I have? Well, I have a tie child, and a tie is better than, here's bad moves. By the way, every red move is a bad move. This is a bad move. Everybody has bad, look, everybody has bad moves. Everybody has bad moves, bad moves, bad moves, bad moves. Everyone has that. So I don't want to take those moves. I don't want to give the person a win, but I don't mind giving them a tie. So a tie says, I don't have a winning move to make, so I can't win the game, but a tie is better than losing, so I'll make the tie move, okay? So tie is better than losing move to make. And a draw is an interesting, some games, not tic-tac-toe, but some games what we call a loopy, which means there's a loop in the tree. The game tree is not a tree, actually a graph, and you're moving around in a circle. So a draw position is one that says, I have a lot of bad moves. Remember, these red ones are really bad moves, but you don't have to take any of them because you can just stay in this draw area, this kind of draw world above, and never make a move. That's a losing move. You never be forced. So it means I can't force to win or be forced to lose. We also keep track of remoteness. Remoteness is something that as we're solving the game, as we're writing code to walk the whole game tree or game graph, we write down remoteness, which is the distance to the best win. If you ever played a chess puzzle, it'll say white to mate in 4, black to mate in 6, that kind of thing. So that means total 6 moves or total ply to be made before the game is over in perfect play. So we write that down and we store that so we'll have remoteness for the future, okay? So remoteness is useful for the computer opponent to be able to play really well. Otherwise, it just plays and moves in a random way. So we need to store remoteness for our computer player. Okay, that's it. I want to open any questions about that. This is just a theory, and this is a little dry, but let's actually get juicy in the next slide. So first I'll pause for any questions, and I'll check the chat. And note that this is different than combinatorial game theory. They don't care about win, lose, tie, and draw. They care about how much you'd win by. Oh, I won by 3. I won by 7. I don't care about that. If you win by 3 or 7, it's the same game to me. So Othello, I only care about you win. Basically, I win. It's kind of like considering all the win by values from 1 up to 64. All of those are considered wins. I don't care how much you win by. And all this game optimizes for is winning fastest, where in combinatorial game theory, they'd win with the most points. They would make the move that gives you the most points. I don't actually care about that in our system. I just care that you win, and you win fastest.
Would Go be considered combinatorial?
Go is certainly a combinatorial game. In fact, people have considered Go end games. In fact, some Go end games are combinatorial. Go is certainly computational, but Go end games are considered combinatorial, which is very interesting. But yes, Go. There's a whole books on this. David Wolf. Look up the name David Wolf. He's written some books about Go end games with a combinatorial spin on it. All right, so we're back to here. So now here's where the fun of Zoom works out. And normally I would do this if I were doing this as like an outreach event. If I would have visited you, then I would have had all of you in a circle or all of you in chairs, and I'd have you pair up. We do this all the time. I do this for an outreach day every year. We're obviously not doing that this year. So let's actually talk about how to do this together. I have 12 participants. I would like to open up to folks to play this together. I think that'd be really fun. So let's go to breakout rooms. I'm gonna make 6 breakout rooms, 12 people. What I want you to do is play this game twice in a breakout room. I want you to play once going first and play once going second. And if you have time, go play. But I'll maybe 5 minutes, maybe. I think there's a way I can choose how that is. 6 breakout rooms. Here we go. Create. Okay, here's the rooms. And I'm going to set this up. I'll be thrown in a room too, I believe. Okay. Here's how the game works. This is a game called 10 to 0 by 1 or 2. On your turn, we start with a pile of 10 coins. Okay, 10 coins. And you can do this by annotating, by the way. You can do this lots of different ways. You can do, if I click annotate, let me do this here. I often start by just drawing something on the screen. And I often do like this. So I'll say, okay, here's 10 numbers. Here's this, here's 5, and here's, oops, that's 6. I drew 6 and 4. Okay, I think I can erase one of these guys. Yoink. I'm still in draw mode. Okay, here we go. Yeah, all right, there's now 9. All right, so I get you 10, and what you do is you, boy, this is slow. Okay, boy, you go, click, click. Okay. Whew. Pile of 10 coins, whatever. On your turn, you subtract 1 or 2 from the pile. The goal is to make the last move. So this game is actually combinatorial because you want to get the last move. But we can solve this too. It's a small enough game, and you just have numbers as the position. Position is just numbers. The moves are just numbers. You make a move of 1 or 2. Your position's a number from 10 to 0. So here's an example game. Starts at 10. Anna goes first. Anna says, I'll take 2 to make it 8. Now the title is 8. Bob says, I'll take 1 to make it 7. By the way, you can play this without writing anything now. You just, in your head, close your eyes and say, all right, 1 to make it 7. That means take 1 to make it 7. Anna says, okay, now it's 7. Anna says, I'll take 2 to make it 5. Now it's 5. Bob says, I'll take 2 to make it 3. Now it's 3. And says, I'll take 1 to make it 2. Bob says, I'll take 2 to make it 0. And Bob wins. So in this game, here's the fun thing. Did Anna win? Sorry. If Anna went first and Bob won, then does that mean this game was a losing game and they played perfectly? Or was it a winning game? Anna, at some point in here, made a losing move, and then Bob had it. And then Bob played perfectly all the way down. Or even more possibly, it was a winning game. Anna made a blunder some point, maybe at the beginning. Bob had a winning position. Bob made a blunder. We call this a fumble. Bob made a fumble. Now Anna had the ball. Then Anna made a fumble again, giving it to Bob, who eventually kicked it across the goal line. Who knows what happens? This is what we're doing. We solved this game to see if we solved this game to see if this particular instantiation of it was perfect play or who messed up when. So I'm going to open up this thing. I want you to play twice. Play once going first, once going second. The goal is to get the last move. Does everybody understand the rules of the game? Okay? And you can play with you can annotate in your breakout rooms. You can make marks and erase them. You can just say this thing. Take 1 to make it 8. You take 2 to make it 6. Take 1 to make it 5, etc. Okay? You understand? All right. So breakout rooms begin. You're going to play twice. And in the normal thing, I would have walked around the rooms to make sure you're doing it, but there's too much in and out. I'll just play and I'll close the rooms out in a couple minutes. All right, here we go. Go.
Hey.
Hey, Omid.
How are you?
Pretty good. How are you doing?
Yeah, I've been talking. I've been thinking about it. How to win.
Yeah.
It's very interesting. All right.
Yeah, it's pretty cool. You want to start?
Okay. So I go 1.
Okay, so it's 9, right? Because we started with 10. Okay, so I go 2, so it's 7.
So it's so you go 2. Now it's 7.
Mm-hmm.
I got 2.
Okay, so it's 5. I go 1, so it's 4.
Okay, I go 1, so it's 3.
I think I lost.
Yeah.
Yeah, okay, I go 1, so it's...
I got 2, I won.
Yeah, all right.
Now you start.
Okay, I go 2, so it's 8.
You got 2, so it is 8. I go 1, so it's 7.
Okay, I go 1, so it's 6.
You go 1, so it's 6. I go. I go 1, so it's 5.
Okay, I go 2, so 3.
Ah, go on.
Yeah, I know.
So, so is the person who starts has an advantage, or how does that work?
Yeah, I think so.
But what if you started with 2, right? And
Yeah.
I called 1. What if I called 2 instead of 1? Then we have 6 left.
Yeah.
Then what do you
So
do?
then, like, if I call 1, for example, we're gonna have 5, and then you can call 2, and oh, yeah, so it's gonna be
Yeah.
3, and then like whatever I call, it doesn't matter. You're gonna win. So
Yeah.
I think you can still win.
So you start 2. I should have called 2. So I guess it's the start that give an advantage. Like if you start 2, I call 2, I have advantage. If I call 1, you have advantage.
Yeah. So I think it's like, yeah. So I think like if at some point like I call 2, then you have to call 2 early, so that at the end,
Yes.
I feel like it's like, yeah, it's like it depends where you call 2, like where the second person calls 2, if the first person calls 2.
True.
Kind of.
I like it. It's very like mind stimulus, It's like
Yeah, it is pretty cool.
Yeah. Do we have to go back, or he will bring us?
I'm not sure about that. We can just go back.
Oh, it says remaining, because I think when you go back, it still counts till 1 minute. Like you see the top. It counts.
Oh yeah. It says 26:48.
Well, let's
Right.
play, let's play one more game.
Okay, yeah. Let's play. You want to start?
Okay, I will go 2.
Okay, I go 1, so it's 7.
So you go 1, so it's 7. I go 2, so it's 5.
Okay, I go 2. So
That's
3.
3.
It's like the same as last time, I think.
Well, yeah, I noticed the goal is basically it's like you need to aim to end at 3 and it's your turn, right? No.
Yeah.
And
So you
yeah.
Yeah, so you need to have like your opponent to end at 3.
Yes. Yeah, which makes
Yeah.
it easier to think about. So you have only 7 to think about how you divide these 7 numbers, like let's say positions to move. You are moving on
Right.
these 7s, right? You either move on here or you move on here, and then the next person will move here or here, right? Like
Yeah. So I'm thinking about it now. So like if you need your opponent to end at 3, like you have to think even like far before that. Because I
yeah,
feel like it depends like how you start still.
yeah. I think it definitely depends. I think it depends on not the person who makes the first move, is the first, like the person who make the second move. Like
Yeah, probably. So
I mean, yeah. I mean, you can still make a mistake in the middle, but
yeah, I mean, yeah, I feel like because like once you get to 3, it's just like obvious, actually like once you get to 5, like the person who is at 5 and he makes a move, if he's at 5, he's gonna win.
yeah.
Like if I'm at 5, I'm making a move, like I just gonna do 2, and then you're gonna be left with 3.
Oh, okay. That even makes it easier. Now we are thinking about only 5 positions rather than 7. So
Yeah.
if I get to 5 first, I guarantee that I'm gonna win.
Yeah, and also like if you're at 4, you can also say 1, and then it's also gonna be 3 for the next person.
Yeah, but like you get, like usually is that when you get at 5, like you get at 4 by the other, like if I get at 5.
Oh,
I
you're right. Yeah, it's like, yeah, the only way. Wait, actually, for yeah, because I don't know, like, because how can you get at 5? You can get to 5 if you were at 6, if the person before you was either at 6 or at 5, right?
I think if I get at 4 and 5, I have advantage.
Yeah,
And if the
exactly.
person get as 7 and 6, I have the advantage as well. So I don't need to stop at 7 and 6.
Right. Yeah, it makes sense.
That's interesting.
It makes sense. It kind of makes sense. Yeah.
Yeah, I think the time is like feels like Oh wow, this is okay. We have to leave, I think.
Okay, yeah.
Oh, we have to- Okay. Yeah, back.
Okay, welcome back, everybody. I hope that was fun. This is usually a lot of fun. And by the way, I hope you get to introduce yourself to your neighbors. Sometimes people don't forget to do that. So make sure you tell your name to the person you're playing with. So I now want to open this up. People turn their videos on if they're comfortable doing that. And let's talk. Let's have a group conversation. First of all, we're going to ask two questions. What's the value of the basic game of 10? If I start this game, do I want to go first? Therefore, it's a winning game. Or is it, I want to go second, therefore it's a losing game. So is it a winning or losing game? And what would my strategy be? Given any winning position, what was my strategy be? If you knew both of those things, you could always win the game. Because if you're winning and you had that winning strategy in your back pocket, you'd always go first, use your strategy, make the perfect moves in any stage, and you never lose. So I need to know whether this is a win or lose, and what the winning strategy is always. Does anybody have any days? Does everybody win both games and have some? I heard some people talking about odd numbers. I wanted to hear some of that strategy. What are we thinking about there?
We were just I guess I was just kind of getting started with the game. I wasn't entirely familiar with it, but it was a very simple one.
Okay, all right. Does anybody have some more ideas?
Yeah, so I mean, we didn't think it through, but it was kind of obvious that if you're at 5 or you're at 4, and it's like your turn right now, you're gonna win.
Oh, so it's 5 and 4 are winning positions. Okay, sounds good so far. Yeah.
So basically, and it also means that the person who had turn before that, he's at losing position. So it's like, if you were at 6
and 7,
not at 7 though. Oh wait, yeah, it's 7. But it
I
depends
think it's
on
3,
it
6,
depends on
and 9 are the losing position, and winning position is 2, 4, and 6.
Well, everything but 3, 6, and 9. I think you're saying.
Yeah,
so
exactly.
So let's try. That's a really interesting conversation. 3, 6, and 9. You claim that 3, 6, and 9 are losing positions. What's your argument? I like it, by the way, but I don't know. I need to hear an argument for it.
I think I have a strong argument for 3, but I don't really have I don't have any evidence to support the losing positions on 6 and 9. The reason I come up with 6 and 9 is just it's just the multiples of 3 basically. So
Interesting. No, I like where you're going with it. This is great. So let's actually draw the game tree. Let's go over here. Let me put this here. Here we go. 0. Okay. And what can move to 0? A 1 and 2. Can you guys see what I'm drawing on the corner? And then 2 can go to 1. And I'm hearing a 3 in here, and 3 can go to 2 and 1. And then the 4 can go to 3 and 2. See this? I'm drawing a little tree. Now, let's actually start labeling things with the colors. If it's 0 and it's your turn, have you won or have you lost? Like here in this example, Bob was at 2. Bob made the winning move, but then it's Anna's turn at 0. Did Anna win or did Anna lose at 0?
Anna lost.
Anna lost. So 0 is a losing position. Does that make sense? If you have 0, that means the other person made the winning move. Is that okay?
Mm-hmm.
So what does that mean? Remember our definition before? Who remembers the definition? Let's go back a slide. Can I do that? Can I click on this and go back a slide? Watch this. Click on this window. Boop, boop. There. See this slide? Based on this, oh, actually, look, I can have both since I wrote in the margin. Look how nice I am. I wrote in the margins. I don't overwrite up anything. If you have a losing child, what are you? What's 1 and 2? Anybody?
Losing child, you're on a winning position.
Right. So 1 and 2 are wins. And I think many of you agreed with me. Does that sound right? So if you're at 1 or 2, you're going to win. You just take 1 or 2 and you win. Is that okay?
Mm-hmm.
Now, let's look at 3. 3 has 2 winning children. What does that look? Which of these 4 pictures on the left does that look like? If you have all winning children, what's your value?
You're losing.
You're losing, right? You see how this is? We're just backing it up. So now 3 is a losing position. And if I keep doing this, I can try this here. Let's go here, 5. So here's 5. And 5 can go to 4 or 3. And 6 can go to 5 or, 4. That's okay. So now, and then, so then I have 7, and 7 goes to 6. And 8 goes to 6 or 7, and then 9 goes to 8 or 7, and 10 goes to 9 or 8. Okay, here we go. Let's see if we can draw loses. So if 3 is a lose, that means every parent of 3 is a what? If your child is a lose, who are you?
Winner.
Win. So all the parents of 3. So I'm going to write W here and W. See that? And now let's look at 6. 6 has 2 winning children and only winning children. Therefore, 6 is a
Losers.
Right? And look at this. 0, 3, 6. Let's keep going. So now because of that, if I just follow the same thing up, this means 8. Yep, 8 and 7 are wins. You see how easy this is? And I go back up over here, and I grab this, and I say 9, which has 2 winning children, is a lose. Lose. And therefore, look how pretty this is on my little picture on the side. 10, which has a losing child, is a win. Look at that. Isn't that neat? So 10 is a winning game. You want to go first. I want to go first. And I want to say 1. Look, I want to say 1 as my winning move. Then, whatever the other person says, what's my strategy? I need to have a strategy so that I can always apply this to any position. So if I'm at 8, what do I do? If I'm at 7, what do I do? If I'm at 5, what do I do? If I'm at 4. So give me a strategy. So it sounds like we know that the game's a win. Got that. We've labeled all the loses. They're all multiples of 3. So then how do I always do that? How do I always move perfectly? So I'll give you an example.
You always subtract to match those the 3, 6, or 9.
Oh, tell me that. Give me an example. What do you mean by
so that? if I was 10, I would subtract 1, and I would stay in a winning position because they would choose either 1 or 2, and they would go to 8 or 7. And
right.
8 or 7, I would always choose the number that would make my opponent be the number 6.
Sounds good. So let's do a simulation. I'm at 9, and I say 1 to make it 8. What do you say?
I would say 2.
Aha. If I say 2 to make it 7, what would you say?
1 to make it 6.
Look at that. It sounds like you're saying the opposite of me.
Yes.
Because the opposite of 1 is 2, opposite of 2 is 1. The sum of those is always 3, and it sounds like between the two of us, we're always subtracting 3 away from the count.
Yeah.
So I had a 9, subtract 3 is 6, subtract 3 is 3, subtract 3 is 0, and then I continue to have the 0, and I lose. So in one sentence, we are going to summarize this game. You ready? Go first, comma, say 1, comma, then go opposite. Huh? Perfect game. We solved the game. Okay. See what the first part, can you guys see this bottom part of my slide? Can you see the bottom part of my slide? I'll show you this little part of my slide. This says, never lose again. You will never lose this game again in the rest of your life. As long as you always go first, always say 1 and go opposite. In fact, even if you wanted to lose, if you just follow that rule, you couldn't lose. How about that for a fun thing? Okay. Let me now take you to the next thing. So you say, well, Dan, that's a trivial little game. How about the real game you played? This is the game of tic-tac-toe. If you haven't played this before, it's a game. It's also called noughts and crosses. And the goal is to get 3 in a row. So you draw a board like this, and you place an X somewhere. And your opponent draws an O. Then you place an X, and your opponent draws an O. You keep taking turns. You can't draw over their opponent. So you can't put an X over another X. You can't put an X over another O. You can't put an O over an O or an O over an X. You can only put in a blank spot. And your goal is to get 3 in a row, either vertically, horizontally, or on the 2 diagonals. Okay, so there are 8 ways of winning here. Now, what I've done is, remember that color coding the value moves before? I color coded the value moves here. This is a system I've done to show you, here are the 3 colors. X goes, by the way, in this game, X goes first. I'm just wrong. X goes first. And X went here, and O went there, and X goes here, and O goes there, and X goes here, and O goes there. Now it's X's turn. Well, let's look at it. If X goes here, do you see why this is a winning move? Because if X goes here, that's 3 in a row. Okay, so X wins by doing that. Do you agree? So I color code that circle with a value. I call that value moves, and I actually color code that circle with the value of moving to that square. So if X were to go there, it would win. If X goes here, X loses. Why is that a losing move for X? What does O do to win?
Bottom center.
Yeah, bottom center, right? O goes here. So that would be bad for X. It's a losing move for X. Why is this is a tie move for X? Why is that? I block O. What does O do for me?
Block you.
O blocks me. Then I go here and nobody's won. And that's a tie. So you see how this beautiful picture shows you the value of playing tic-tac-toe. This system can teach you how to play tic-tac-toe. If you play it enough, just watch the yellows and greens and always go green but never go reds, and you'd always win that game. If you just keep doing that, you'll see the pattern over time. Isn't that neat? So now I want to show you a demo of my system. This is, can you guys see this window? This is tic-tac-toe. But, by the way, I show you here, this says, misère is tricky. Misère means the opposite. Misère means the opposite. So 3 in a row loses. It's a different game. It's not the same game we're talking about. We're talking about normally tic-tac-toe, except that 3 in a row loses. So it's really bad. I want to do a time check. How much time do we have, Wamid, to see if we have enough time to do another breakout room?
We have up till 5.
Okay.
It's like 4:45 right now, so 15 minutes.
15 minutes. All right, so let's do this. Let me just click for you. You tell me what to do. We're playing the Misère game, okay? You guys tell me what to do. This upper left we'll call upper left, top center, top right, or northwest, northeast. You can tell me, and I'll make the moves for you, and we'll see and the system is going to play against you, okay? Let's make sure here, play here, and computer. So the computer's going to play perfectly, okay? All right, you guys tell me what to do, and the goal is to win. You can, by the way, I just give you a prediction. You can only tie this game. So if you tie this game, consider it a win. There is no win available. The computer's going to play perfectly. There's no way that you can win this game because the computer's playing perfectly. Okay? Here we go. What do we got? I'll turn this off. You guys tell me what to do. Center. All right. Center. All right. Computer does that. Your turn.
Top center.
Which one?
Top center.
Top center. All right, here we go. Go ahead. Remember, you don't want to get 3 in a row, so don't go here. You want to go anywhere but there. Go ahead. Anybody else? This is all a group.
Bottom right.
Bottom right. I love it. Good move. Nice. Okay, go ahead.
Top left.
Oh, nope. That would win the game. That would be bad.
No. Oh, I
Center right. Center right.
Yes, you got to here. That's the only one, right? You can't go there. You can't go there. You got to be here, right? So go here. Okay. Oh boy.
Game over.
We lost. See? They won. All right, maybe that was bad. Let's try again. Maybe the center was bad. Let's try another one. Try another position. Go ahead. Give me something else.
Upper left.
Here, there we go. Here we go. Okay, let's try it now. All right, go ahead.
Bottom right.
Bottom right. Perfect. Okay, good stuff. Okay, here we go. Give me something.
Center right.
So, all right, sounds good. Here we go.
Top center.
Top center sounds good.
Top center,
Okay.
yeah.
Okay, good. Yep. And then, oh boy. Wah, wah, wah. All right, let's back up one. Maybe if I go here instead. Let's go here instead. How about this one? That's better. That's better. Okay, here we go. And then wah, wah, wah. Let's back that up. Okay, back it up 2 spots. How about here? Okay, let's not go there now. What's a better one than going here? Maybe that wasn't so good. Go somewhere different than that one. What's better than that? Give me another option. You can't go here or here. Okay, so go somewhere else.
Bottom left, I guess.
There it is. There. Keep the corners. Own the corner. All right. Give me something else. Can't go here. There. I'll just go here, right? That's the only place to go. Yep. And then here. And then wah, wah, wah. Okay. So we start to see that this computer's playing pretty good, right? And we start to ask ourselves, what is the perfect play? Is this even possible? We say new game. The predictions say I should be able to tie. Do you want to see the answer? It is the middle, but watch this. Watch how I play it. Here we go. Wherever they go, watch the only move that's possible. Can you see this? If they go left, I go, what's the word?
Right.
Right.
Well, I mean, but give me like a more general term. If they go here, I go opposite.
Opposite.
Watch. Go up there, I go opposite. Huh? There, and then you go opposite. Look at here. Look at here. We did it. There's our tie. Nobody wins. Congratulations. So now I ask you, can you summarize this game so that you never lose again? How do you never lose this game again? Tell me. Summarize it for me.
If you start in the middle and play
Go first. Go first. I gotta say go first.
And opposite.
Then go in the middle, and then go opposite. So even though these games are like a million miles apart, remember this game's about 10-0. This game's a tic-tac-toe. It's the same idea, right? Go first, do something, and then go opposite. Go first, say one, go opposite. Go first, go in the middle, say opposite. Isn't that fascinating? 2 games that are actually the same game, really, in some sense of that perfect play. That's fun. This is a tie. That's a win. Anyway, the point is it's kind of neat. And by the way, I should show you this one. Let me go back to here and say human versus human, and maybe ask a question. If I play both sides of this, if I were to go in the top right, I would be making a losing move. What color dots should I see after I make a losing move? Can you guys tell me? If I make a losing move, then I've lost the game. The opponent has won. What should they see for the colors of their dots? If you're a winning position, what does that mean? You should at least see at least this color. What's that color?
At least one green.
At least one green, right? Because if they have a winning position, they have at least a winning move. We talked about that. At least a winning move. These are all the colors of the moves, not the positions, right? Watch. Here we go. And here are the greens. You see where the greens are? So the greens are kind of in the edges, okay? If I were to, let's try this, go in the top center, look where the greens are. Kind of the opposite here. Interesting here, right? To think about this, okay? So let's memorize this again. Let's memorize if I were to go here, the greens are kind of in like a square, right? And like a little diamond, like a baseball diamond. Let's remember that, okay? As I go back. Let me go back to my slides. So I visualized the tic-tac-toe answer key. Remember, the game is a tie. We agree the game is a tie. And Misère tic-tac-toe is a tie, right? So I made a box that's a yellow square. And then, you remember all the values of this? Let's go back here. Remember this? Let's go back to the beginning game. This has yellow in the middle and then red around it, right? So watch how I visualize it. Yoink. You see what I did? See how I did that? It's a recursive picture. I drew a picture of 8 red squares, or yellow in the middle. Look at that. Same thing, right? And if I were to go in the top right, what happens? I would get a green diamond, right? Now watch what happens here. A green diamond. See how I recursively draw the picture in that square? So this is my visualization. I created this as a visualization of how to think of the game tree. And if I did this for the whole game, you'd see all the possible situations. Isn't that interesting? So this is like an answer key. If you had this answer key, you could walk around and pull this out and have an answer key, which I think is really fun. Neat, right? Okay. Phew. So I want to share with you that only 9 minutes. We have solved Connect 4. We have the game of Connect 4 available. I want to show you my website. This is the website called GAMESMAN Uni. And this is our website that has, look at this. Here's Misère, tic-tac-toe. It only plays 2 players, but if I turn on the values, look, if I show you the values, next move, and the hint, watch what happens. Look, this is the Misère game, just like I showed you. So it's online. So the world can play this game. It's not just me and my system. Look, I play here, and look, there's the diamond of green. Remember the diamond of green? There's the diamond of green. So if you had this up, you could have this on your phone, be tapping away, and be playing perfectly. And, say with me, never lose again. Okay, that's part of the theme of this talk. So I solved Connect 4, which was an amazing game. It took 30 machines, 8 cores, 1 week to do it. And we figured out it's a winning move, and it's a winning move. It's a winning position. The winning move is in the middle. If you go to the neighbors, it's a tie, and if you go to the edges, it's a lose. And if you do happen to go to the edges, this is the response. See this little recursive picture? These are the response things. So if you go to this left edge, then any of these 4 moves are the possible responses for that. Kind of beautiful and kind of neat as a way to think about that. All right, fun. So GamesCrafters is my research and development group that I've had since 2001. We're going on 20 years. We average 20 students a semester. They work in teams of 2, and they put games in our system. It's really wonderful. Most return take more senior roles. For example, team leads. We have 70 games in our system. Let's see if I can show you an example of what it looks like. Let me bring it over here, and let me show you this one. Watch it. Let me show you what it looks like. Background, XM, GAMESMAN, GAMESMAN. Yeah, that'll work. Watch what happens. Here we go. Look at this picture. See all these games? These are all the games we have in the system. And so you can play some of these games. If you want to say, well, let's play the game of, what's a fun one? This game is Sim. Let's try this one. Sim is really interesting. Yoink. And I say new game. And I say play now. I hope this has been solved before. Let me see. Yep. Here's it. To win, you avoid making a triangle of your color. Move. You take turns. This is K6, by the way. This is like 6 vertices, and they're all connected to each other. So this is called K6. And your job is not to make a triangle. And only a triangle, I mean not a triangle like a small one, but a triangle from like corner to corner to corner. So this is a triangle in here. And you want to avoid making a triangle of your color. That's the goal of this game. Okay? So let's try. And by the way, let's see. Let's turn on value. Let's turn on value moves. And it turns out it is a losing game. So we can play 2 players. Watch. If I play human versus human, the first player goes there. Look, all green. Doesn't matter what you do, you're going to win this game. Isn't that fascinating? So we'll go this one, just random one. All red. Doesn't matter what you do, you'll lose the game. So I'll go here. And now notice some are red or some are green. You want to look like this. The red is, the bright red is my move, and dark red is the value. So it's my turn. I want to choose probably a green one. So I'll choose this green guy. I'll choose 3 horizontal lines. Oops. Here. Okay, there. And now it's a losing. So I don't going to do. Blue's going to lose either way. Here. Blue's. And now it's red. Red only win here. Okay, and you keep playing this game. Now it's Dan Red's turn. Up. So look, I made a triangle. See that? I made a triangle. That wasn't so good. I can undo and try to not make a triangle. Let's not make that triangle. Let's see if we can dodge it. Keep dodging it. Oh, I got to keep playing the green. I'm blue. Can't help but make a triangle. Watch. Can't help but make a triangle. And by the way, it tells you, look what this. It tells you how much you should win by. You should win in 4 moves. So I should win here. There's my, what? Here. You should lose in 3 moves. So I'll go here. Up. That was bad. Probably better moves than that. Let me see if I can I avoid a loss if I go here? No, that's a move. How about here? That's probably pretty good. Yep. I should win in 2. How about there? Now I got to lose. I'm going to lose in 1. Look, this one makes that triangle. This one makes this triangle. And this one makes that bottom triangle. Nothing I can do. Isn't that neat? So this is just an example of many of the games we have in our system to show off. Kind of fun. In summary, board games are exponential. And so has been the progress and speed of computers. Therefore, every few years, we only get to solve one more ply, one more move we can make. One by one, we're going to solve them and or beat humans, but we'll never solve some games. See this game Go? We call this the hardest game out there because each of the squares can have, it'd be blank, white, or black. There are 19 square or 361 positions, so that's 3 to the 361. You know how big 3 to the 361 is? This big. That, my friends, is a big number. So big that it's more than the number of atoms in the universe. So even if we could solve it, we wouldn't have any place to store it. So we're never going to solve this game. So my group focuses on strongly solving games, board games. University of Alberta folks focus on weakly solving games because they're really big. They're much bigger than me. It would be way too hard to strongly solve checkers, but I only care about strongly solving games, so I have the answer from now on till the end of the lifetime. That's it. So I've solved tic-tac-toe, Connect 4, smaller games. I have the answer. Nobody else. It's not like, well, I have a probability that I might. No, I always would win if you play my strategy perfectly. That's it. Thank you very much, folks. Thanks for coming on my talk. Woo!
Thank you, Professor. Appreciate it.
I think I have some time for questions and answers now. If you want, we can do some of that.
Actually, we have like a couple of minutes if you don't mind. I'm sure.
I'd love to. Yeah, there's a couple of people talking in the chat. I'll stop sharing, by the way, and that's the end of my presentation, and we can just talk and have a conversation. Great.
I would like to ask you just one quick question. We did not touch on chess. Is chess a winning or losing game?
Hasn't been solved yet. Okay. Some people argue that it's too big, but end games have been solved. If you've you can load in end game databases. They call them table bases, and you can load those in. Actually, often a chess playing program will automatically load it. So if they solve the next version, like now I have the 8-piece end game or the 9-piece. Once they solve that, it goes to the server, grabs it. So your local chess playing program that you get now will usually load those in and play perfectly once you get past some number of positions. But right now they certainly but it's only like 7. The total number of positions is 32. So we're way far away from getting to a solved chessboard. But and by the way, it's exponential. Every next ply is another factor of 20. So we're never going to get. I don't think we're ever going to get to a full solve. But there have been some people who think that they have a solve. I try to read some people who have done a soft solve on later games and prove that they can prune the tree in different ways. We still think that it benefits going first, but I haven't heard whether it's a winner, a tie, or a draw. And by the way, chess considers they have stalemates, but they have stalemates that are ties and stalemates that are draws. If you have a position where you can't move any piece and you're not in check, but you can't move any piece, that's called a stalemate. That would be a tie. You can't move. Mm-hmm. If you just have 2 kings wobbling back and forth, that's an infinite draw. They also call that stalemate. So their stalemates encompass both my ties and draws, but they call them the same. I mean, for me, a tie or draw is the same. It's equal points for both players.
Sure.
Other questions?
Is there, for a strong solution, do you basically have to do that through brute force no matter what? Or are there other ways to approach the strong solution?
Yeah, that's a good question. I say strong because I want to be able to have an answer for any student who happens to walk down the tree and go there. Now, some people say, you know what we do? We do a just-in-time thing. So we'll prove that we won't visit everybody, but if the student never got near that area, I would quickly farm off a quick solve of that so I have it. So there's a way to be clever about it so you don't have to store everything and prove. By the way, the reason that you can prove it without having to visit everybody, which is what chess does, you can weakly solve. If you remember, to prove it's a win, all you have to prove is the existence of a winning move, which means a losing child. There's a million other children you could ignore as long as you prove that one of those children is losing. To prove it's losing, you have to fan out to everybody. So to lose, prove that all the guys are wins. But for every win, you only have to choose one move. So you use AI to say, well, make the strongest move and then follow that and see if that reduces a lose for that opponent. Therefore, I'm a win. Therefore, I tell my parent I'm a win, and you keep doing this. So that's what strong solves do, is they kind of ignore all these other guys out there. But I want to be able to just have it, store it, and be done with it, rather than like, let's be clever and only store a fraction, and blah, 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 blah. There is a very interesting thing, which is a points of exploration that I've thought about, but I haven't implemented yet for our students, from my students' point of view, which is, what if you did a machine learning approach, which is, your machine learning says, what's machine learning good at? Classification. So you classify positions and by the way, they usually run them on tic-tac-toe to kind of, do these kind of warm-up exercises. So you imagine writing a classifier that figures out for any position, it figures out what it is, but sometimes it's wrong, right? Remember, classification is sometimes wrong. Sometimes it thinks this is a stop sign for my Tesla's auto-driving car. So sometimes things get fooled in classification, right? Sometimes it thinks that a bird is a cat, that kind of thing. So what you could do is you could write a classifier that's a smaller piece of code to do that, okay? And then enumerate all the tic-tac-toe positions, find out when the classifier is wrong, and then store those. So you've got a classifier in one hand, and then all the ways the classifier were wrong in the other hand, and between the two of them, I have a perfect solution. So you could strongly solve it without using it all deep search. I mean, you have to strongly solve once to know what the answer is. But once you have the answer, you could store it in a more efficient way by storing the classifier and storing the exceptions to the classifier, and you'd be done. You'd have the same thing. And that might be more bits or fewer bits than the original. Our group has been spending 20 years to think about how tight can we pack this in, not just using gzip or compress, but could we actually throw stuff away to have a really tight version of the file? Because these things get exponentially big. If I talk about Connect 4, it took us 4 terabytes. 4 terabytes! That's a whole hard drive just to store one game. So as I go to bigger games, how about 40 terabytes? I mean, I don't want to, pay $2,000, $10,000 to store one game. So we've worked a lot hard on really pinching this down to the smallest possible representation and thinking about that. But another way we haven't explored, but would be really interesting, is thinking about this classifier. How many bits for the classifier? How many layers is the machine learning model? And then how many bits to store the exceptions? And that can be really clever. We still want to. It's still to know that it is an exception, you had to have done it by yourself. So you still have to store it. I'm just talking about efficiently try to store the final answer. But good question, Mark. Thank you for that. Other questions?
Yeah, I have a question. So I often hear popular or maybe like unpopular opinions that quantum computer is gonna break some of cryptographic algorithms. So I guess, is it also going to allow us to solve more problems?
Well, actually, the beautiful thing about quantum computing is it's like trying to decode a password, right? Think about to decode a password. A normal serial computer has to try every one, right? Try it and try it and try it. A quantum computer is in all the passwords at once. If you have the bits set up right, you could actually have all the possible superpositions at once. So the answer is, that's a fascinating thing. Here's what I think about game theory. To know that solution is perfect, you still had to enumerate all of them. You still have to go through, just like I was talking about before, machine learning, you have to go through them all and check, okay, that one, check. But the fascinating thing about it, so it does, okay, how do I say it? If you tell me I have a miracle machine which gives me the perfect solution to chess, I have to, it's not an NP-complete problem. NP-complete problems are, here's the answer, I randomly give it to you, and I can verify that it's the answer in polynomial time. That's what that says, to be NP-complete. Right. But if you said, Dan, this miracle quantum computer gives me the solution to chess, how do I verify that's perfect? I have to, A, have stored it and solved it, and then have to go through one by one to make sure you're making the right move or that you've declared all the losing positions and losing positions. So how quantum interacts with game theory isn't so clear, because even if you told me I have a quantum computer that plays perfectly, how do I know that? I don't know that. I'd have to go through all the cases to check it all. So I have to like exponentially visit them all anyway. And I'm telling you, I don't have time to exponentially visit them all anyway. So how can I verify that your quantum computer that's able to like solve it instantaneously or with, sometime, that it was perfect? So it's like you'll create a quantum solution, but I won't know if it's right or not. That's the problem, without having to take the original time in the original serial machine or parallel machine to do that in the non-quantum way to test it. So maybe you're clever. It's like, oh, have another quantum tester. Well, that's already makes my brain hurt. So answer is.
So just to make sure I got it correctly, you're saying that quantum computer can just give you a solution, but you're not going to be. Like, it's not going to give you every single solution. Or
well, a solution is given a position, you tell me whether it's win or lose, and given a position, you tell me if it is a win, what the winning move is. So that's what it means. That's what it means to have a solution, is Given any random position, whether it's win, lose, or tie, or draw, and if it is win or tie, what the move is that is the winning or tie or draw move, the one that's not losing. Once it's losing, you don't care, because remember, losing, all the moves are the same. They're all losing. Who cares? But if anything but losing, I need to know what that move is. So your quantum solution would have to be all of that. It'd have to be not just, it wouldn't just be, it's not like a traveling salesman problem, here's the path, I'm done. It is, here is the strategy for future inquiries of other games of that. So it's a much bigger thing that it would be delivering to me. It would be delivering a system that I could query and say, well, here's a position. And it would give me back, here's the answer, here's a position. So it's much more complicated than just, here's the solution to the traveling salesman, here's the solution to your password, I've cracked your password. That's a different thing. So you'd have to have somebody else to verify that it was right. And again, that takes just the same amount of time it took to solve in the first place. So it's harder to figure that out.
A question?
Yeah, dude.
Peter, yeah.
It's really interesting.
Yeah. Hi, thanks. But actually, I think I had to thank Artem for bringing this up because I was wondering if it's like, is it theoretically possible to build a virtual precog?
What does that mean?
Like a precog is basically a person who kind of has, it could be either an absolute or kind of like an almost supposedly one could assume that the precog has the ability to discern or perceive certain probable outcomes from branching off from the current moment or a given situation. But
I mean, like in some yeah, go ahead. In some sense, a system like my system knows everything there is to know about the game.
Mm-hmm.
So my system, remember, my system played perfectly in Misère Tic-Tac-Toe. It plays perfectly in all the games that it plays because it knows the whole tree. Like it is God, and it knows everything. So it would say, if I give you the human at losing position, you could say it's a precog because it'll say, I know you're going to lose because there is no way that you could win that game. You'll always make a losing move. Giving me the computer winning position, I always make a perfect move. I'm making a winning move. You'll have a losing position. It'll always be win, lose, win, lose. Me, computer, win. You, human, lose. Me, computer, win. You, human. Every time, all the way down the tree. For however big the tree is 1,000 moves. It knows the future in that sense. So in some sense, because it knows the whole state, it knows everything about it. So it's less about a precog, but it knows the world, and you don't. I know how to play 10-0 perfectly. So if I'm going to tell you, if I'm going first, I'm going to win. And by the way, I didn't tell you this part about this. I can actually make you win. Did you guys know this? Any game that's impartial, I didn't tell you this part. Any game that's impartial, I can force you to win. Wait, watch this. We're going to play 10-0. Ready for this? 10-0. The day before, and you are going to win this game, even if you don't want to. Even if you don't want to, you're going to win this game. You understand what's going to happen? Pretty cool. Okay. Go ahead. Go ahead. So I say 10. I say 1. Now you have 9. And you think you're going to lose, right? Because 9 is bad. Right. Remember, it's 0, 3, 6, 9 is bad. But in fact, I'm forcing you to win. Regardless of what you do, I'm going to force you to win. Go. That's 9. Your turn. Go ahead, Peter. Make a move.
I would like to say 8, 7, 7.
It doesn't matter what you say, by the way. I have all the power.
Okay.
1. Okay. All right? It's now 8. 2 to make it 6. You're still going to win. Even though it looks like you're going to lose, you're going to win this game. Go ahead. So I'm a precog. I know you're going to win this game. I just know. Go ahead. Give me a number.
I did. Actually, it's a 2.
2. Okay, so now you're down to 4. Ready? 1 to make it 3. Oh, wait, sorry. I have to do this right. I have to do this right. Sorry. No, 4. Darn it. I did this wrong.
Wait,
I did this wrong. I did it wrong. I played wrong. I played wrong. You can win. If you say 2, then I have to win. Darn it. We'll go back. Okay. Darn it.
Wait, let's go back. Yeah.
Yeah. No. You have to go first. Sorry, you have to go first. You have to go first. No, you have to go first. I'm sorry. We're starting again. You're going to win this game, but you have to go first.
Okay. I'll go with 1. So that'll give. Wait, what am I doing?
9. That's right. Perfect. I'll
give you a 9. Yeah.
Right. I say 2 to 7. Go ahead.
2 to 7.
Basically, I'm going to give you a 1, and you can't help it. I'm going to give you a 1, 4, 7, and 10. That's the path. So if you have 1, you can't help but win, right? I'm going to give you 1, 4, 7. I'm just telling you. I'm precogging 1, 4, 7, 10. It's your turn. You said 1. You said 10. You said 1 to make it 9. I say 2 to make it 7. You have 7. I'm going to give you 4, whatever you do, because whatever you say, I'm saying opposite. Go ahead.
Okay.
I'll wait. 2. I say 1. You've got 4. Go ahead. I'll wait. You're going to have 1 in a second. I'll just wait a second. You've got 4.
what do I have right now?
4. And you're about to have 1, but you can't help it.
2.
1. Now you got 1, and you just won the game. See? So this is a fun game where I have full control. If you start by 10, then I force you to, because basically it's 1 4 1 4 7 10. You can't help it. And I played it around perfect. And if I want to win, then I just start on 10. I say when it's the same thing, and I always give you 0 through 6 9. Neat, right? So in some sense, if you say think about the precog space, because I know the whole world, I know the future, right? If I play perfectly, then but it doesn't matter. That's what's nice about this. It doesn't actually matter what you do. If we had a game that was 100 moves deep, if I had a winning position playing perfectly, it wouldn't even matter what you do. It's very helpless from the other side of this. It's very helpless. Kind of like when I play against the computer on chess. I can't beat my computer in chess. My computer's way too good. I've never beaten it in the maximum mode. It's a little helpless. This is what this is with you and me playing this game.
But it becomes increasingly difficult to be a precog if you're putting more variables in. If you're factoring in more variables in. Let's say it's not going to be the same game anymore. It could be a different game. Maybe something a little more complex. And
well, I just have to store more. Whatever the computer does, it just stores more, and then it knows it all. So it's really, yeah.
I think that's the answer to Peter's question.
In other words,
will we have in the future somebody who will or a precog or something that will know the future when you ask about something, right? Basically, that was the question. I think that's basically we are thinking about a really, 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 really small version of a problem. We're talking about chessboard. It's really small, and as you said, really limited variables.
Right, small space. Yep.
Right, and it's still not really solved to know all the moves and whether it's a winning or losing game to that degree. Then when we think about the whole world, it's a much bigger board and much more possibilities.
And you have to ask about what is winning in life. Does winning have the most money? Does winning have the most happiness? Exactly. Does winning mean you made the most people happy? If everyone optimized for making everybody else happy and making the world better, that'd be a pretty nice optimization problem. And then so you can think about a lot. Most people say, "Oh, let's make the most money." Yeah, that's very short-sighted. It's about healing the world and making people's lives better. So I think, in some sense. You might have the future robot. We're talking about AI, but the future robots, if you program them with the goal of optimizing happiness and optimizing satisfaction, that would be, greatest utilitarian, like Immanuel Kant. That would be really interesting. Yeah, go ahead.
I was just thinking, because I was wondering if there was already because it almost seems like. Did we get to that point? It almost seems like we have some kind of for example in the video game, I was wondering if it's possible AI software is recording all the players' signature movements, and I
think you're
let's say it's an imperfect AI system, and then. Because there was an NVIDIA card that someone could use to kind of basically store the player's play style, and then he just goes in front of the door to get some pizza. Game the chipset plays the game for him while he's trying to get pizza.
No, you certainly could have in a video game. No, in a video game, you could certainly have a computer be memorizing my style. I get that. When a goblin comes over, I shoot the goblin or I run away from the goblin, and it knows what I do, so that I could say, now play like me, and it's learned what I do and I play like me. It's I've played the driving games for a while where you make one lap, right, and then the second lap you're racing yourself because it remembers what turns you did, and you did that. So in some sense, you could do the same kind of thing. You could have a system that learned how you play a particular game or all games and then says, play like me, play like Dan. Well, Dan is cautious, but then at the end of the game, he's very aggressive and then cautious again. You could imagine somebody learns what those strategies are, semantically stores those, and then tries to play like that. It would be very interesting.
Yeah, but I would also think about a reverse scenario in which the entire game itself, the computer software, it uses the data it collects from the player, and then gives the enemy NPC a basic blueprint of how they could deal with the player, such as me. I I was wondering in reverse how if that we could make an AI system that could manipulate these play styles and decided, okay, but it's not going to be a perfect AI system, but it's going to use that information to kind of like even the odds, like because it knows what that player tends to do. It's going to try to compensate for that, even though the player is going to try to adjust his move set.
You could do anything. I mean, here's the point. Fun of this is that once you have the tree and you know the answer, that you're God, you know everything. And so if you watch a player do something, you could remember what they do. You know that when it was good, when it was bad. That's the part that's important here is you need me to tell you when it was good and when it was bad, to store that, to then learn, okay, well, you're good except when we press you. Like I played my son in chess a lot. And what I used to see is, as an example in chess, when I would threaten him with the piece, he would always block it. There are like many things you can do when you're checked. What can you do? There's like 3 or 4 things that are official. You could either move the king out of the way, just run. You could block it. Okay. Well, forget checking, but imagine I'm about to capture a queen. I'm about to threaten a queen. Okay. You could either block the thing, put your other piece in the middle. Okay. You could interpose. It's called interposing. You could capture the piece that's doing it. Or here's what's fun. You could check somebody else. Like often what a gambit is, where I give you some pieces because I'm actually taking over the game and coming from the side. So I was like, oh, why is he giving away his queen? Well, because he's actually mating you with his 2 rooks. My son, when he was first learning, never did that. So you could, he never knew. He always responded locally is what I mean. He always responded, if I'm threatening his queen, he'd always move the queen out. He wouldn't even think to block it or to capture my queen. He'd always just move his queen out of the way or something, okay? So I learned, when he did it to me, he blew him away when he did it to me and threatened my queen. There was one game where I played with, rather than deal with that, I said, take my queen. I went over here with the double rooks to try to win the game. So I ignored that, thinking that I'll actually get better to sacrifice the queen to give my brother double rooks. So you could have a system that learned that person in that kind of scenario, having played enough games to know their pattern, if I know that you're never going to double threaten me with the double rooks, I'll be able to beat you even more. I mean, the point is my system has to beat you all the time. But if I were losing, you could actually, remember, not all losing moves are the same. I could have a losing position that in theory, my son should beat me, but he's not going to see this particular reaction that if I were to, if I get my queen threatened, he won't see that I'm going to double his up with the rooks. He won't know to do that. He won't know to do that. So if I threaten his queen, I know he'll move away because I know he won't, even though he could win by bringing the rooks in, he won't do that. So you could imagine a computer player that's even better than it is now, meaning it can even play better given a losing position, which it should always lose, right? The human should always beat it in a losing position. But I'm saying that it would do even better if it knew the pattern of a user, like you're saying, to then exploit it. I know that you're always going to move your queen away by threatened, not come back. Even though that's the way to beat me, I would still lose the game because I know you're going to run. That'll put you on. I know what you like. It's almost like an older player watching a younger player. I know what you're going to do. You're going to, when you play a younger kid, they're always going to run it away. They don't know to double up and amplify the pressure to check my queen. And maybe that trade is better for me, but they won't know it. They always just run away. Early players always just run away. So you can imagine a losing chess player making use of that and being a stronger player as a losing player is what I mean. If it's winning, it's going to win all the time. But from a losing point of view, it can actually be better if it knew the pattern. Long answer to a short question.
This is definitely like really interesting, and we are way over time.
Yeah, way over time. But this is so much fun. This is so great.
Fun. It's definitely so much fun. And again, thank you so much for this speech. It was really interesting, intriguing.
No, my pleasure. I had a great time.
Yeah, thank you all for joining. Appreciate it.
Wonderful.
Have a great rest of the day.
Good stuff. Thanks again for inviting me. That was really great. Nice to meet you all.
Thank you all.
Good stuff.
Thank
Too bad we didn't do this in person, but I had a good time anyway. Thanks again, guys.